very important point. Let me repeat this point again. See, for the synchronous motor or synchronous generator, we are going to define the power factor, which is called as the theta. Power factor angle is called theta, which is angle between the V and IA. It is same for with the synchronous motor or synchronous generator. This is a small correction that we have to make it here. I have did a small mistake there. So we can say clearly, over-excited synchronous motor. Over-excited synchronous motor means, I already told you, in the over-excited synchronous motor is going to operate in the leading power factor region, and synchronous generator working in lagging power factor means synchronous generator working in lagging power factor means synchronous generator working in lagging power factor means it is working in the over-excitation. So therefore, whether for over-excitation case, whether it is a synchronous motor or synchronous generator, they are always going to deliver the reactive power. So they are always going to both deliver the reactive power, and induction motor always going to absorb the reactive power, whereas a synchronous motor, they can absorb the reactive power, they can deliver the reactive power. So but only induction motor will always accept they are going to always accept the or absorb the reactive power. If I draw the characteristics between the armature current and the field current for the synchronous motor, whenever the excitation is changed but the mechanical load is a constant, then we are going to get in this format. As you can see clearly here, as this is the graph that you are going to get when you are not going to keep any no load. At no load you are going to get graph in this panel, which is, you can see this like an inverted curve. See, whenever the field current increases, the current magnitude value decreases. It will decreases, and the power factor angle decreases, but the power factor increases. You can say clearly up to unity. Here it is a lagging nature. But after reaching the unity power factor, if you again increase the excitation, the field current increases, so the armature current, the IA value will increase, but the power factor will decrease because the power factor angle increases. So we can say clearly that here, whenever the field current increases, the current decreases up to unity power factor angle decreases, so therefore power factor increases. But again, if you still increase the field current, we can say that simply the armature current increases and the power factor angle increases, so power factor will decrease. So therefore the graph between the IA and IF you are going to get in the term of the V shape, and the graph between the power factor and IF you are going to get a inverted V shape. This is for the no load case. But if you want for the load cases, if you want to go for the load cases, then definitely this graph is going to shift to the right side. Again, if you go for higher load, again this graph is going to shift to the right side. So here also you have to shift the graph to the right side, again for the right side. So always this is for the no load condition. If you want for the load condition, just you have to shift the graph to the right side, both the V curve and also the inverted curve. Just you have to shift it to the somewhat to the right side because of armature reaction. So therefore, whenever you go for the loads, at the loads, you have to just shift the graph to the right side, both the V curve and also the inverted V curve. So as when load is kept, armature reaction is going to come. So whenever you are going to keep the load, the armature reaction is going to come, means as the armature current is not equal to 0, armature flux is going to present. So field flux and armature flux are going to interact with each other. So therefore the armature reaction is going to occur. So extra IF is required to compensate it. So we need extra amount of IF to compensate that armature reaction. So therefore the graph is going to shift to the right side because we need a small amount of extra IF. So therefore the graph is going to shift to the right side because of this armature reaction, because we need extra amount of IF to compensate this armature reaction. So whenever the load is increases, so whenever the load is kept, definitely the armature reaction is going to occur. So we need extra IF to compensate this one. So therefore the graph is going to shift to the right side. So a 3-phase silent pole synchronous motor is connected to an infinite bus. So whenever a 3-phase silent pole synchronous motor is connected to an infinite bus, it is operated at no load, at normal excitation. The field excitation of the motor is first reduced to 0. It is reduced to 0. It is first reduced to 0. Means we are going to reduce the excitation and then increased in the reverse direction Generally, gradually, then the armature current first increases. See, whenever you are going to decrease the field excitation, you can see clearly in the lagging power factor, the armature current will increase first and then it will decrease steeply. As I have already told you, you have to see, they have not mentioned whether it's the leading power factor or lagging power factor. So you have to always see in the lagging power factor. And if you decrease the excitation, the armature current increases. and if you increase the excitation in the reverse process, the armature current will decrease. So this is the point that I have already shown in the lagging power factor region of this diagram. So therefore, a three-phase 7-pole synchronous motor is connected to an infinite bus. It is operated at no load at the normal excitation. The field current of the motor is first reduced to 0 and then increased in the reverse direction. Gradually then the armature current first, it is going to first increase. Whenever you are going to decrease the excitation, definitely the current, you have to see only the lagging region. So therefore it is going to increase first and then it is going to decrease steeply. Then we can say that the resultant air gap flux. So let me tell you, the resultant air gap flux is equal to phi f plus phi a. Suppose if phi f is equal to 0, because if is equal to 0, suppose if I made excitation is equal to 0, then what is going to happen? Suppose if I make excitation is equal to 0, so therefore phi f is equal to 0, and then I want this constant one, if suppose this is increased because of load is increased, then what is going to happen? I have already told you, P is equal to V into Ia into cos theta. Definitely, what is the constant one? You can see clearly in this case, the mechanical load is a constant, so P is always constant and V is a constant. Then definitely, if Ia is increased, then definitely the cost should decrease. Then only we can say that the overall value is a constant. See, P is a constant, V is a constant. We need this factor to be constant. So therefore, Ia into cost should be always equal to constant. If suppose Ia increases, then definitely the power factor should decrease. Suppose if Ia increases, then phi A will also increases. So phi A increases means it is going to generate the reactive power. So therefore, we can say, phi A increases means we can say that we need phi A to make this phi A air gap constant. So therefore, we are accepting phi A from external. So therefore, Q increases means if we are going to take taken from the bus. So this is a very important point. See, I have already told you, if field winding is sufficient, field winding should give supply, field winding should always give the flux for the air gap flux and also for phi A. If phi F is giving for both air gap and also for phi A, then we can say that in that case, the phi F is generating the constant flux and also is generating the reactive power. But if you are taking phi F from external to make phi A, then definitely we can say that here we are taking the reactive power from the outward region. See, if this is a plus means we need phi F and also we need phi A to get the constant air gap flux. So we need phi F and we need phi A. So this phi A is taken from the reactive power from the bus bars. Suppose if phi F is sufficient, suppose there is a minus here, then phi F then phi F itself is giving phi air gap and also phi A, then definitely we can say that there we are going to generate the reactive power to the bus bar. So whenever the phi F itself is enough to compensate the air gap flux and phi A, then we can say that there we are generating the reactive power from that machine. If suppose we are taking phi A from external to get the constant flux, then we can say that it is said to be it is accepting the reactive power from the bus bars. So finally we can say that whenever the field winding is 0, so whenever the field winding current is 0, because If is equal to 0, then definitely we need a constant air gap flux. So we need phi F from external, so we have to take the reactive power from the external. So as this value increases, the reactive power also increases. From external we are taking more amount of reactive power from the external. But I have already told you P is equal to V into I into cos theta. So P is a constant, V is a constant, and as phi A increases, then definitely Ia increases, then cos theta should always decrease. By changing polarity of field winding, rotation won't change, and to reverse the directional rotation of synchronous motor, any two terminals of the armature are reversed, which is called as a negative phase system. See, I have already told you, by changing the polarity of field winding, rotation won't change, and to reverse the directional rotation of synchronous motor, any two terminals of the armature are to be reversed, which is called as a negative phase system. Same concept I have already told you. If you want to do the reverse rotation of the synchronous motor, here you don't have to change the polarity of the field winding. If you change the polarity of the field winding, just the fixed poles polarity are going to change. Again, they are going to rotate in the same direction. Instead of that, you have to interchange the supply. You have to interchange the any two terminals of the supply. Then the overall phase will differ. Then the resultant flux is going to rotate in the reverse direction. So therefore, this motor is also going to rotate in that reverse direction. So therefore, we can say that if you want to rotate the synchronous motor in the reverse direction, you need to change the phase sequence of any two windings. Then you are going to get the reverse NS. Then the rotor is also going to rotate in that direction itself. So this is the thing that you have to always remember. Just by changing the field winding, the polarity of the fixed buds are going to change, but they are going to get in the same direction of the ns. So we can say that simply, if you want to change the potential of the synchronous motor, then you need to change any two terminals of the supply. This is called as a negative phase sequence. For a silent pole synchronous motor, just remember this equation. It's very much useful for a small number of questions. So for silent pole synchronous motor, the reluctance torque is called as which is Vt square by 2 omega s into 1 by xq minus 1 by xd, where xq is called as the quadrature axis reactance and xd is called as the Dirac's axis reactance, and omega s is nothing but 2 pi ns by 60, and Vt is called as the supply voltage or terminal voltage, and here is called as the reluctance torque, and delta is the angle between the Ef and V. All these things we have already discussed. So Tr is equal to Vt square by 2 omega into 1 by x2 minus 1 by xt into sine 2 delta. So Tr is equal to Vt square by 2 omega s into 1 by x2 minus 1 by xd into sine 2 delta. So Tr is equal to Vt square by 2 omega s into 1 by x2 minus 1 by xd into sine 2 delta. So we can say that Tr is said to be reluctance torque, and Vt is called as terminal voltage or supply voltage, and delta is called as load angle, or basically it is in the terms of the electrical degree, it is a phase angle between the Ef and V. So delta is called as a load angle, it is in the terms of electrical degree, it is a phase angle between the Ef and the V. Then what is the condition for maximum Tr? So if you want the maximum, just do the derivation with respect to delta and equal to 0. So therefore we are going to get dt by d delta is equal to 0, and delta is a variable and we have to assume the remaining values are constant. Then do the differentiation with respect to this one. Sine 2 delta differentiation is 2 into cos 2 delta is equal to 0. Then if you solve this one, we are going to get 2 delta is equal to 90 degree. So delta is equal to 45 degree. So at this phase angle, at this load angle, with respect to F and V, we are going to get the maximum reluctance torque in the silent pole synchronous motor. The expression is Tr is equal to Vt square by 2 omega s into 1 by xq minus 1 by xd into sine 2 delta. So Tr is called reluctance torque and delta is called as load angle or electrical degree in the terms of Ef and V. So now we will discuss one more important concept, which is called as the effect of varying the mechanical load of synchronous motor with constant excitation. Suppose if I am going to vary the mechanical load of synchronous motor with a constant excitation, if you see clearly, this is the reverse cross of the previous one. In the previous one, we have kept the mechanical load as a constant, but we have changed the excitation. But now here it is a reverse of the previous one. Now we are going to change the mechanical load with the constant excitation. Then what is the graphs that we are going to get? What are the consequences because of this effect? We are going to study one after the another. So as you can see clearly, this is the phasor diagram that we are going to get for this one. Let me explain in a very detailed manner each and everything. As I already told you, is a synchronous motor. So whenever the load increases, then definitely we can say that the amount of active power is also increases. So whenever the load increases, the active power increases, but the excitation is a constant. So whenever the excitation is a constant, the flux is a constant. So therefore EF value is always constant. So EF is always constant for all the time irrespective of the load variation. So now we can see clearly. Then as the load increases, what are the parameters that are going to get changed? The current, the armature current is going to get increased. If the load is more, the amount of current taken is also increases. So therefore we can say the current intake is also going to get increased whenever the load is increases, because the power intake is also increases. So now then we can see that this synchronous motor we are going to connect to. So this synchronous motor we are going to connect to 3-phase balance supply. So therefore it has a constant bus bar voltage. So V is a constant. Then we can say that whenever the excitation increases, whenever the excitation is a constant, so F is a constant. The supply bus bar voltage is also constant, so V is a constant. As the load increases, the current IA is also increases. So based on this, now we are going to draw the phasor diagram for each and everything. So I already told you, in a synchronous motor, the expression is V bar is equal to F bar plus J into IA into XS. Then this is the voltage. So always V is always going to lead the EF irrespective of the current drawn by the synchronous motor. So let me take this as the voltage V and this as the EF. Then in the first case, let me assume the current in this direction. The current is in the leading forward with respect to V. So therefore we can say it is the leading power factor because the current is leading the IA. So always we have to define the power factor of the synchronous motor or synchronous generator with respect to theta. Theta is the angle between the V and IA. The IA is leading the V, it is called as the leading power factor. Now this is IA1 then what is the J into IA1 excess? This is the where you are going to get, which is perpendicular to this one. So therefore you are going to get like this, which is called as the, this is for the first case, this value is for the first case. So therefore if you add this one, which is IA1 excess, because this line is perpendicular to this one, so therefore IA1 excess, if you add these two vectors, you are going to get V. Similarly, if I increase the load, then definitely the current will increase. So IA2 value will increase in this format. So therefore now, then this will be EF, and this is called as the IA2 into excess. So this is called as the IA2 into excess, and this is perpendicular to IA2. So therefore if you add these two vectors, you are going to get V. Again, if I increase the load, the current will increase, but now it's a lagging power factor. Whereas here, leading power factor, it is a unity power factor, and now it is a lagging power factor. So therefore this is the value of EF, and this is the IA3 excess, because you can see this line is perpendicular to IA3. So if we add these two vectors, we are going to get V. So what we have understood now, if I increase the load, then definitely the value of the IA is increasing, the value of the IA is increasing, and the value of the delta, which is the phase angle between the EF and V, this called the torque angle, it is also increasing, as you can see clearly from this phasor diagram. This is delta 1, this is delta 2, and this is delta 3. As you can see clearly, the delta is also increases. So whenever the load increases, the load is increasing in the downward direction. So whenever the load increases, the current IA increases, the delta increases, and also we can say in the leading case, if you see clearly, whenever you increase the load, the IA increases, the power factor angle decreases, so power factor increases, and the delta also increases. This you can see clearly from this one. But if you go for the lagging portion, if you still increase the load, then the delta increases, IA increases, and the power factor angle increases, so power factor decreases. So these are the concepts that you can easily understand. So IA3 is greater than IA2 is greater than IA1, because as the load increases, the current intake is also increases. So now we can summarize that as the load increases, the current IA increases, and also the value of delta increases, as I have already shown in the graph itself. So V is called as the constant supply voltage or busbar voltage, it's always constant. Then what is the power factor? Power factor is the angle between the, it is the cos of angle between the V and IA. So it is called as a theta. Theta is nothing but power factor angle. The theta is called as a power factor angle between the supply voltage and the supply current. So whether it is a synchronous motor or whether it is a synchronous motor or generator, always we are going to define the power factor with respect to this theta itself. So now let me give you some important points regarding this concept. Suppose when synchronous motor is operating at the leading power factor means IA is going to lead the way with constant excitation. If the mechanical load is increased, then I already told you, if the mechanical load is increased means the mechanical output power is also increases, means we can say P is equal to VIA into cos theta. Definitely the current IA will now increase. So therefore current IA is going to get increased. So therefore I have already told you, if the mechanical load is increased with constant excitation, EF is always constant. So therefore as the load is increased, the power factor angle decreases, so power factor increases, the delta increases, and the power factor and Q are inversely proportional, so Q decreases and the armature current increases because the load is increased. So these are the points that are going to happen whenever you are going to increase the load in the leading power factor region. So whenever the synchronous motor is operating at leading power factor with a constant excitation, if the mechanical load is increased, then the power factor angle decreases, power factor increases, delta increases, Q decreases, and IA increases. Suppose when the synchronous motor is operating at lagging power factor with constant excitation, if the mechanical load is decreased, means you have to go in the reverse case, then definitely we can say that the IA decreases because load itself is decreasing and the power factor angle decreases. So power factor increases and then delta decreases, and the power factor and Q are inversely proportional, so therefore Q also decreases. As PF increases, so Q should decrease. So these are the things that you always need to keep in mind. The phasor diagram, if you keep in mind the phasor diagram, then you can answer any question that they are asking in the examinations. If your synchronous motor connected to AC mains is running at full load and unity power factor, if its shaft load is reduced by half with field current held constant, its new power factor will be, as I have already told you, this is same as the previous concept, the concept that we are going to discuss right now. See, in this question they are saying that we can say that they are saying that basically the field excitation is a constant, but initially it is operating at UT power factor. If the load is suddenly decreased, means we have to go in the reverse process, which is it is going in the leading power factor, and the power factor angle increases. So therefore the power factor will decrease. So therefore we can say that its new power factor will be leading and delta will decrease because the phase angle between them is going to get decreased. So therefore we can say that a three-phase synchronous motor connected to AC mains is running at full load and UT power factor. If its shaft load is reduced off, means the load is decreased, then with the field current held constant, means we can say that its new power factor will be leading and the delta is going to get decreased. This you can see clearly from the phasor diagram itself. So let me give you the final conclusion of each and every aspect of the synchronous motor and the synchronous generator. So if you remember this table, definitely at least one question will be asked in any common examinations. See, I have already told you this is the graph between the armature current and the field current. So this is the armature current with respect to field current. It is like a V curve. Similarly, the power factor curve is like in this inverted V curve. This is the graph between the power factor and the IF. So the graph between the PF and IF is nothing but inverted V, and the graph between IA and IF is nothing but V graph. So I have made into three regions: under excitation region, normal excitation region, over excitation region. So U means under excitation, NE means normal excitation, and OE means over excitation. As I have already told you, under excitation means EF into cos delta is less than V. Normal excitation means EF into cos delta is equal to V, and over excitation means EF into cos delta is greater than V. So these are the three conditions that I am going to use. See, whenever the field current is increased, we can go from normal excitation to under excitation to normal excitation to over excitation. So whenever the field current is very low, it is under excitation. Whenever the field current is very high, we go for over excitation. As you can see clearly in the over excitation, the synchronous generator is going to operate in the lagging region. The easy way to remember is here G is there, so here also there is a G. So always in the over excitation, the synchronous generator is going to operate in the lagging region, whereas the synchronous motor is going to operate in the reverse one, which is called as the leading. Similarly, in the under excitation, the synchronous generator is going to operate in the leading region, and the synchronous motor is going to operate in the lagging region. So if you remember this one, then you can go for each and everything. Just do the reverse of this one. Here lagging means it is a leading. Here leading means it is a lagging. So this is a very easy way. So we are going to define this lagging and leading with respect to a theta, which is called as the V and IA. So we are going to define this power factor like leading and lagging for synchronous motor and synchronous generator with respect to a theta. This theta is the phase angle between the V and IA. So for lagging, for a synchronous generator, lagging means the IA is going to lag the V. And for synchronous motor, leading means the current IA is leading the V. Similarly, for synchronous generator, leading means the current IA is leading V. And for synchronous motor, lagging means the current IA is lagging V. So for both the motor and generator, we have defined the power factor with respect to theta, which is the phase angle between the V and IA. See, under the over excitation, for both synchronous motor and synchronous generator, always the armature reaction is demagnetization. So whether it is a synchronous motor or synchronous generator, at this over excitation mode, they both are going to behave at they both will have the same armature reaction, which is called as the demagnetization. So in the over excitation region, both the synchronous motor and the synchronous generator will have the same thing, which is called as the same armature reaction, which is called as the demagnetization, and it is going to deliver the reactive power. So synchronous generator is going to deliver the reactive power, and it also going to deliver the active power. Whereas the synchronous motor, it is going to deliver the reactive power, but it is going to absorb the active power. Synchronous generator is always going to deliver the reactive power, and it is also going to deliver the active power. Whereas synchronous motor, it is going to deliver the reactive power, but it is going to accept the active power. That is the reason synchronous motor is operating in the leading region. So therefore we can say at no load condition, means if you are not going to keep any load for the synchronous motor, at the over excitation region is going to act like a leading power factor. So we can say it is going to generate the reactive power. It is going to deliver the reactive power. So because of this reason only, we can say it is called as the synchronous condenser, because at no load, at the over excitation, synchronous motor is going to act like a synchronous condenser because it is generating the reactive power. So it is used for improving the power factor. At the over excitation, I have already told you EF cos delta is greater than V. Whereas here, in the under excitation, we can say that whether it is synchronous motor or synchronous generator, they both are having the same effect, which is called as the magnetization. The armature reaction is magnetization in nature. Whereas the reactive power, they are going to absorb. For both the synchronous motor and synchronous generator, they are going to absorb the reactive power. For synchronous generator, it is going to absorb the reactive power, but it is going to deliver the active power. So listen carefully. This synchronous generator is going to absorb the reactive power and it is going to deliver the active power. Whereas the synchronous motor, it is going to absorb the reactive power, but and also it is going to absorb the active power and reactive power. Synchronous generator is going to absorb the reactive power but delivers the active power. Whereas the synchronous motor, it is going to absorb the reactive power and it is also going to absorb the active power. So this is a case that you always need to keep to understand this one. So therefore we can say that always, and if you see clearly at no load, synchronous motor at the under excitation, it is going to operate in lagging region, means it is going to absorb the reactive power. So that is the reason at under excitation the synchronous motor can be used to compensate the Ferranti effect, because it is going to act like a inductor, means it is going to absorb the reactive power. So therefore we can use it as a compensator to compensate the Ferranti effect. So under excitation, EF cos delta is less than V. Whereas at the normal excitation, both the synchronous motor and the synchronous generator, they both are going to operate at the unity power factor, means the phase angle between the V and IA is equal to 0, so power factor is equal to 1. So therefore we can say that the armature reaction is always cross magnetization because of this two. So always if the synchronous motor or synchronous generator operating at normal excitation, they have the same effect, which is called as the cross magnetization, and EF into cos delta is equal to V is called as the normal excitation. Whenever the EF into cos delta is equal to V, it is called as the normal excitation. Suppose if you are not going to keep any load, if you are not going to connect any load to synchronous motor or no load to synchronous generator, then delta is nearly equal to 0. So this is the thing that you can easily visualize. So if you assume delta is equal to 0, then for under excitation E is less than V, for normal excitation E is equal to V, and for over excitation EF is greater than V. So if you assume at no load for both synchronous motor and synchronous generator, then if you substitute delta is equal to 0, then we are going to get EF is less than V. At the under excitation, at normal excitation we are going to get EF is equal to V, and at over excitation we are going to get EF is greater than V, whenever we are assuming that there is no load. So this is the conclusion regarding each and every V curve and the inverted V graph. So this is the oral thing that you always remember, because definitely at least one question will be asked from this one. So now we are going to discuss the one more important concept, is called as the starting methods of the synchronous motor. So as I have already told you, the synchronous motor is not a self-starting motor. So by using some techniques, we need to give the starting torque. If we give the starting torque, then it can rotate on its own. But only thing is, it requires the starting initiation. That is the thing which is required by the synchronous motor. In the same case, we have studied the same similar case in the induction motor also. Their single phase induction motor is not a self-starting. So to make it self-starting, what we have did, we have added an extra. So we have added an extra auxiliary winding. So with the help of this auxiliary winding to the main winding, it is going to behave like a two-phase motor initially. After some time, after reaching certain speed by this rotor of the induction motor, then we are going to take out this auxiliary winding. That is in the case of the induction motor. But here in the synchronous motor, we need to do something to initiate the starting torque of the synchronous motor. Means the starting torque is equal to purely 0 for synchronous motor. We have to make it non-zero by using some techniques. Those techniques that now we are going to study one after the another. So by using the auxiliary motor, means we are going to use some extra motor to initiate the torque, means to initiate the rotation. Then we are going to remove this one, then it is going to get on its own. So listen carefully. Whenever you are going to give three-phase supply to the stator and the DC supply to the rotor, it is not going to rotate initially. We have to give extra movement, initial movement from this auxiliary motor. An auxiliary motor can be DC motor or induction motor. It can be any type. It is going to give an initial amount of rotation. After that, we are going to remove this auxiliary motor from here. Then it is going to rotate on itself own. So we can say that this is called as the initiation. We are going to give an extra movement, initial movement. So in this method, initial supply is given to auxiliary motor. So by using auxiliary motor, synchronous motor is operated near to synchronous speed. At this instant, supply is given to stator, so rotating poles are established, and DC supply given to field winding. And DC supply is given to field winding, so fixed poles are established. At one instant, magnetic locking is obtained between the stator and the rotor poles. Thereby, rotor is going to rotate in synchronous speed, and supply can be disconnected to the auxiliary motor. So what I am trying to say is, we need to couple both the auxiliary motor and the synchronous motor. Then we have to give supply to the auxiliary motor, so therefore it is going to initiate the rotation of the rotor. Then we have to give the supply to synchronous motor. The stator we need to give the AC supply, and the rotor we have to give the DC supply. Because of AC supply on the stator, there will be rotating magnetic poles. On the rotor we are going to give DC supply to the field winding. It is going to produce the fixed poles. So now, as the rotor is rotating, there will be a magnetic locking between the stator and the rotor. Then it is going to rotate further. After that, we need to remove the supply of the auxiliary motor. Then we can say that we have given initiation for the rotation of the rotor with the help of auxiliary motor. After magnetic locking, we are going to remove the supply for the auxiliary motor. So this is the overall process in which we are going to make the starting torque is not equal to 0 for this synchronous motor. Means basically we are rotating it initially. Then we are going to remove the auxiliary winding whenever it is going to rotate with the help of magnetic locking of the AC supply of synchronous motor. So in this method, initial supply is given to auxiliary motor. So by using auxiliary motor, synchronous motor is operated related to synchronous speed. At this instant, supply is given to stator, so rotating poles are established, and DC supply given to field winding, fixed poles are established. At one instant, magnetic locking is obtained between the stator and rotor poles. Thereby, rotor rotates in synchronous speed, and supply can be disconnected to auxiliary motor. So this is a very important point. See, basically we are giving supply to auxiliary motor. Auxiliary motor can be the DC motor or induction motor. As we are going to give auxiliary supply to the auxiliary motor, it is going to rotate. It is going to rotate as both our synchronous motor and auxiliary motor are connected cascade. So therefore, the rotor is same for both of them. So if one is rotating, the other is also rotating with the same speed. As the synchronous rotor is rotating, what we have to do, now we have to give the supply to the synchronous motor stator, AC supply. And for the field winding which is present on the rotor, we need to give the DC supply. Because of AC supply on the stator, the rotating field is going to get produced, whereas on the rotor, because of fixed supply, we are going to get a fixed poles. As both are going to interconnect, and then there is a magnetic locking between them, so after that, the rotor is going to get continuously. At this instant, we don't need to give the supply to the auxiliary motor because it can rotate on its own. So we have to remove the supply to the auxiliary motor. So this is the basic function of this. By using this basic method of auxiliary motor, we are going to give the initial torque for the synchronous motor. The basic disadvantage of this method is it occupies more space because we are using extra motor. Thus, amount of space required by them is very high, and the cost of the system is very high because we need to buy an extra auxiliary motor in order to rotate the synchronous motor. It's a very severe pain in the neck. Buying one motor itself is very cost, and buying one more is a very severe cost. So we can say it's a severe pain in the neck. So therefore, the cost of the system is very higher. In this method, synchronous motor can't be started with load since rating of auxiliary motor is present, because we are going to give itself the synchronous auxiliary motor only we are going to give initially, so you can't keep the load at that instant. So after removing the auxiliary motor only, then only you can keep the load, whatever the load that you want to keep. So initially you can't keep the load on the synchronous motor. When it's running only, then only you have to keep the load. So in this method, synchronous motor can't be started with load since rating of auxiliary motor is present. Since the auxiliary motor itself is present, then we can't keep an extra load there. But after removing the auxiliary motor only, then only you can keep the load, whatever the load that you want to keep to the synchronous motor. But initially you can't keep it because auxiliary motor itself is there. This is one of the disadvantages of this method. So we can say it is going to occupy more space. Cost of the system is very high. In this method, synchronous motor can't be started with the load since the rating of the auxiliary motor is present. Now we will discuss another method by which we can provide the starting torque to the synchronous motor. This follows by using the damping winding. I have already told you I will explain this one in a very detailed manner in the coming pages. So this is the case. Now I am teaching this one. Why we are going to use the damper winding or damping winding on the rotor. On the rotor we are going to use the damper winding. Why it is used? Now we are going to explain that concept behind that one. So therefore, the first method that we have learned is by using the auxiliary motor, we can initiate the initial torque of the started synchronous motor. Similarly, the second method is called as the by using the damping winding. So this is the starter in which we are going to keep the armature coil. So we are going to give three-phase supply. So we are going to get a rotating magnetic field. And now what we are going to do basically is here, as I already told you, here field winding. So here field winding is there, right? So here we are going to short circuit with the help of external resistance. We are going to keep here, we are going to keep an damper winding. I have already told you I am going to keep a damper winding on the holes of this rotor in this circular manner, and this is called as a field winding. The number of turns of field winding is very higher when compared to the number of turns of the damper winding. This concept also I have already told you. This is called a damper winding and this is called as a field winding. So damper winding arrangement is very similar to squirrel cage rotor winding. In this method, initially three-phase supply given to stator, thereby rotating poles are established. With respect to transformer action, EMF is induced in the damper winding and field winding. EMF induced in the field winding is very high, since number of turns are very high. To protect the field winding from high voltage, external resistance is connected in series to field winding. Damper winding establishes its own flux phi and the field winding induced voltage also establishes its own flux phi f dash. Due to the interaction of the stator flux and the rotor flux, which is phi d and phi f dash, the stator flux is phi 1. Induction motor torque is developed, thereby rotor reaches to near to synchronous speed ns. At this instant, external resistance of field winding is disconnected and DC supply is given, which is called as the fixed poles. And DC supply is given, which is called as fixed poles are established. At one instant, magnetic locking is obtained between stator and rotor poles. Thereby, rotor is going to rotate at the tunnel speed. And induced voltage in the damper winding becomes zero. Induction motor torque becomes zero. During starting condition, by correcting external resistance in the field winding can be protected from high voltages and starting torque can be increased. For starting of synchronous motor, high resistance damper winding is preferred. So therefore, TD is directly proportional to phi into I into cos theta. So cos theta is equal to R by Z. As the R increases, cos theta increases, so TD increases. So basically it is telling that damper winding arrangement is very similar to squirrel cage rotor winding. In this method, initially three-phase supply is given to stator, thereby rotating poles are established. With respect to transformer action, EMF is induced in the damper winding and the field winding. EMF induced in the field winding is very high since number of turns are very high. To protect the field winding from high voltage, external resistance is connected in series to field winding. Damper winding establishes its own flux phi d and the field winding induced, this is induced voltage, it is not included, it is induced voltage also establish its own flux phi f or phi f dash or phi f. Due to interaction of stator flux phi 1 and rotor flux phi d and phi f dash, induction motor torque is developed. Thereby, rotor reaches to near to synchronous speed ns. At this instant, external resistance of field winding is disconnected and DC supply is given. Fixed poles are established. At one instant, magnetic locking is obtained between the stator and rotor poles. Thereby, rotor is going to rotate at the synchronous speed and induced voltage in the damper winding becomes zero because induction motor torque becomes zero. During starting condition, by connecting external resistance in the field winding can be protected from higher voltages and starting torque can be increased. For starting of synchronous motor, high resistance damper winding is preferred, which is TD is directly proportional to phi into I into cos theta. As I already told you, cos theta is nothing but R by Z. As R increases, cos theta increases, so therefore TD increases. So now let me explain this concept behind this one. Now I told you about the theory part. Now I will give you the detailed explanation here. See, basically what we are going to do basically is here. Initially, we are going to give three-phase supply to the stator coils. Then we are going to take this field winding and this is a damper winding. So for field winding, we are going to give some external resistance and we are going to do the short circuit. So this is the damper winding. I have already told you the damper winding has lesser number of turns when compared to field winding. So because of this three-phase supply, a rotating field is going to present in the air gap. So whenever this rotating field is going to interact with the coils, the EMF is going to get induced in them. The EMF induced is directly proportional to number of turns. The number of turns of field winding is higher when compared to number of turns of damper winding. So therefore, the induced voltage in the field winding is very high when compared to induced voltage in the damper winding. As the voltage is very high, the current is also very high. But if you are not going to keep any external resistance, current is very high, so it is going to damage the field winding. That is the reason, to get the less current, we are going to keep the external resistance here. Because the voltage is very high, you may get huge amount of current. So if you want to limit the current, you have to use the external resistance. So you have to keep some external resistance by which you need to do the short circuit. See, now because of that, these are the closed windings, so a current is going to get induced there. So because of these currents, flux are also going to get produced. Let me assume flux produced by the field winding is phi f, and the flux produced by the damping winding is phi d. The cause is called as the cause for this one is the rotating flux, and the effects are the phi f and phi d. So this phi f and phi d, they are going to interact with the main flux, or we can say the effects are always going to oppose the cause. So because of this, there will be a rotation. There will be a rotation of this rotor. There will be a rotation of this rotor. So therefore, it is going to rotate. When this rotation is very good, when this rotation is very high, if it is nearly equal to synchronous speed, then what we have to do is basically we have to remove this external wind. We have to remove this external resistance, and then we have to give a DC supply here. So if we give a DC supply, then the fixed magnetic poles are going to present, and the rotating magnetic field and its fixed poles are going to get magnetic locus is going to get present, then it is going to get at a speed of synchronous speed. Whenever the rotor is rotating at synchronous speed, definitely we can say that there is no relative flux difference between the there is no relative motion between the rotor and the synchronous speed, because both are rotating at same speed. So there is no flux cutting in the damper winding. So we can say that there is no induced EMF in the damper winding, so no induced current in the damper winding. So this is the concept behind this one. So this is the concept behind all this explanation. See, whenever NR is less than NS, so whenever NR is less than NS means it is called as the induction torque. So induction torque means we are going to increase the speed to NS. See, suppose what is going to happen with the help of this damper winding, let me tell you. Suppose if I increase the load, definitely the speed may small. Suppose if due to some external disturbance, suppose if the speed decreases of the rotor, then what is going to happen? An induction torque is going to present between the rotor and the synchronous speed. So therefore, because of that, it is going to increase the torque and it is trying to reach the synchronous speed. If suppose the speed is more than synchronous speed, then the induction generating torque is going to get produced. So therefore, the speed will decrease to NS. So always this damping winding is going to act to make NR is nearly equal to NS at each and every condition, whether load decrease or load increase. So this is the beautiness of the damper winding. So damper winding, with the help of damper winding, we can get the initial amount of starting torque from this motor. So to protect the field winding from huge amount of induced voltage, we have to keep the external resistance. I have already told you. So therefore, we can see that starting torque also can be increased. If you keep the more resistance means we can say more resistance is more power factor. So more starting torque, because the starting torque is directly proportional to starting resistance. In the induction motor, I have already told you the starting torque is directly proportional to resistance of the rotor. As the rotor resistance increases, the starting torque increases. So we try to prefer to use the maximum resistance as maximum as possible to produce the most starting torque. So therefore, the synchronous motor can rotate. So for starting for synchronous motor, high resistance damper winding is also preferred. So we have to connect a huge amount of resistance to the field winding, and also a huge amount of resistance of damper winding, because initially induction torque is going to produce, initially it is going to act like an induction motor only. So I have already told you the induction motor for the starting torque is directly proportional to rotor resistance. So here as R2 increases, then definitely the starting torque increases, because the TD is directly proportional to phi into I into cos theta. Cos theta is equal to R by Z. As the rotor resistance increases, the power factor of the rotor increases. So therefore, we can see that simply the amount of starting torque or the deflecting torque or induction torque will increase in this one, because initially NR is less than NS, so it is going to act like an induction motor. After you are going to give DC supply to the field winding only, then the magnetic locking is present, so it is going to act like a synchronous motor. But up to that time, it is going to act like an induction motor only. So these are the two methods by which we can start the synchronous motor, by using auxiliary motor or either by using the damping winding. So let me tell you some important points regarding this synchronous motor, which are very much useful because at least one question will be asked from this concept. Let me give you some important points which are very much useful for the different types of examinations. In synchronous motor, if the rotor speed is less, suppose in synchronous motor if the rotor speed is less than the ns, so suppose suddenly variation if the speed is less than ns, then EMF is induced in the damper winding because there is a relative difference between them. So because of that, the flux is going to cut the damper winding. So EMF is going to induce in the damper winding. So EMF is going to induce in the damper winding. It is directly proportional to the relative speed. Damper winding establishes its own flux phi d with the interaction of stator flux and the damper winding flux. Damping torque develops, or we can say induction motor torque. With respect to Lenz's law, damping torque opposes its cause of existence. So primary causes relative speed, thereby damping torque acts in the same direction of rotation of motor. So rotor will be accelerated. The rotor speed is less because of sudden load. So we can say that in a synchronous motor, if the rotor speed is less than ns, means suppose I have increased the load, suddenly nr will be less than ns. Then EMF is going to induce the damper winding. This EMF induced in the damper winding is directly proportional to relative speed because there is a difference in speed between the nr and ns. So damping winding is going to establish its own flux phi d, and with the interaction of stator flux phi 1 and a damping winding flux. So damping torque develops induction motor torque. With respect to Lenz's law, damping torque opposes its cause of existence and the primary causes relative speed, thereby damping torque acts in the same direction of rotation of rotor. The rotor will be accelerated and the rotor speed is less because of the sudden load. Suppose if I increase the load on the synchronous motor suddenly, then what is going to happen? nr is less than ns. So there is a relative speed difference between the nr and ns. So therefore we can say because of this a flux is going to cut the relative flux is going to cut the damper winding. Then a flux is going to induce in the damper winding, which is called as the phi d. And this phi d is going to oppose the phi f because the effect is always going to oppose the cause. This flux is because of relative speed, so it is going to oppose the relative speed, means it will try to make the relative speed is equal to 0, means it is going to rotate in the same direction, then only the relative speed will be decreasing. So therefore nr will be nearly equal to ns, means the speed will increase because of the induction motor torque. Because it is going to act like induction motor. Whenever nr is less than ns, it is going to act like a induction motor. The torque developed at that condition is called as the induction motor torque. So therefore the speed will increase. So therefore now it will become nr is equal to ns. So in synchronous motor, if the rotor speed is less than ns because of external addition of sudden load, then EMF in the damper winding, EMF induced in damper winding is directly proportional to the relative speed. Damping winding, the damper winding establishes its own flux phi d with interaction of stator flux phi 1 and damper winding flux. Damping torque develops induction motor torque with respect to Lenz's law. Damping torque opposes its cause of existence. So primary cause is relative speed, thereby damping torque acts in the same direction of rotation of rotor. So motor will be accelerated, the rotor speed is less because of sudden load. So finally I can say that whenever you add an extra load to a synchronous motor, the speed will decrease instantaneously. As nr is less than ns, so we can say that there is a relative speed between the nr and ns. So this relative flux is going to cut the damping winding. So therefore the flux is going to EMF is going to induce in the damping winding and current is also going to get induced there. So it is going to produce some flux, which is called as a phi d, and phi 1 is a stator flux. So they both are going to interact. Always the effect is always going to oppose the cause. The cause is called as relative speed, so it is going to decrease that speed. Means nr must increase to make that speed decrease as per the Lenz's law. So therefore nr increases. As nr is less than ns, it is called as the induction motor. The torque developed at this condition is called as the induction motor torque. So because of this induction motor torque, the speed of the rotor will increase and it will try to make it to ns. So it is called as the induction motor torque. So now we will go for the reverse case. Suppose if the load is decreased, suddenly, then the nr is greater than ns. Again there is a relative speed between the nr and ns. Then as nr is greater than ns, it is called as an induction generator. It is going to act like an induction generator. Now the torque produced at this condition is called as the induction generator torque. It is going to oppose its cause. As per the Lenz's law. The effect is the relative speed. It is going to decrease its relative speed. So therefore nr will decrease and it will make to ns. So this is a concept regarding the whenever there is a sudden decrease in load. So when rotor speed becomes greater than synchronous speed, EMF is going to induce in the damper winding and it will establish its own flux phi. Due to interaction of stator flux phi1 and damper winding flux, damping torque is developed. Induction generator torque, by according to Lenz's law, it opposes its cause of existence. The primary causes relative speed, thereby damping torque acts opposite to the direction of rotation of rotor. So therefore, deceleration is going to get happen. So during hunting, due to presence of damper winding, induction motor and induction generator torques are developed. So whenever there is a sudden change in load, these induction motors, whenever there is a sudden change in load, these induction motors and the induction generators are going to torques are going to establish, and it will try to make NR is equal to NS always. So this is the beautiness of this concept. So finally what I am trying to say is, if the load is increased, the speed will decrease. Then induction motor torque is going to get act in the same direction of rotation of the rotor, then the speed will become NR is equal to NS. Suppose if the load is decreased, the speed is increased, which is NR is greater than NS, then it is going to act like an induction generator. Then the torque developed at this connection is called as the induction generator torque. It will act in opposite to the rotation of rotor, so speed will decrease. So therefore again NR is equal to NS. So this is the case, this is the beautiness of this concept. Induction motor torque and induction generator torque, they will always establish whenever there is a sudden change in load, then they will try to make NR is equal to NS always. So when rotor speed becomes greater than synchronous speed, EMF is going to induce in the damper winding and it will establish its own flux phi. Due to interaction of stator flux and the damper winding flux, damping torque is developed. Induction generator torque, by according to Lenz's law, it opposes its cause of existence. The primary cause is relative speed. Thereby damping torque acts opposite to direction of rotation of rotor, which is called as a deceleration. So during hunting, due to presence of damper winding, induction motor and induction generator torque are going to get developed. Thereby rotor reaches to synchronous speed in the very shortest time. So for prevention of hunting, low resistance damper winding is preferred. So if you want to remove the hunting, just you have to use the low resistance of damper winding. But if you want high starting torque, you need high resistance of damper winding. These things I have already told you. So if you want high resistance of starting torque, you need huge resistance of damper winding. But if you want to remove the hunting, then you need low resistance of damper winding. To get the huge amount of starting torque, you need huge amount of starting resistance. But if you want to prevent the hunting, this sudden change in load, definitely this current should be very maximum in the damper windings. Whenever their resistance is less than low, then the currents will be high, and then only these induction motor torques and induction generator torques are going to get established, and then they will try to make NR is equal to NS. So if you want to remove this hunting, then definitely we need to have low resistance of damper winding, because if the resistance is less, current is huge in the damper windings, then we can say they are going to produce more flux, and then they can make the things happen to make NR is equal to NS. So this is the contradiction that you are going to get. For starting torque, you need huge amount of starting resistance of the damper winding, and you need to prevent the hunting, you need low resistance of damper winding is preferred. Causes of hunting. So what the causes of hunting are, which is due to sudden variation of load. See, hunting means you are going to get the new stable point. Hunting means it is basically you are going to get the new stable point of operation, which is the cause of hunting are due to sudden variation of load. If you are suddenly varying the load, then the new stable point is going to get. So therefore you can say it is due to sudden variation of load, or due to sudden variation of excitation also you are going to get this hunting, and due to any sudden fault, or due to harmonic load turn. So by these effects you are going to get the hunting. So due to sudden variation of load, or due to sudden variation of excitation, or due to any fault, or due to harmonic load turn. So these are the reasons by which you are going to get the hunting. So hunting is going to established because of this process. So these are the reasons by which the hunting is always going to get established in the synchronous machine. So therefore, due to sudden variation of load, or due to sudden variation of excitation, or due to any fault, or due to harmonic load turn, means we can say that basically hunting means a new stable point is going to get obtained because of these variations. And what are the effects of hunting? So what are the side effects of hunting? If hunting is happened, then what are the effects? The machine is going to subject to more electrical and mechanical stresses. So there will be huge amount of electrical and mechanical stresses on the machine. and the surges are developed in the current and the power flow. A huge amount of spikes are going to establish in the current and the power flows, and the rotational losses increases, thereby temperature also increases. So therefore we can say the effects of hunting are the machines, basically the machine is going to subject to more electrical and mechanical stresses, and surges are going to develop in the current and the power flow, therefore the rotational losses increases, thereby temperature also increases. So these are the effects, or we can say the side effects of hunting. The machines is going to subject to more electrical and mechanical stresses, and the surges are going to develop in the current and the power flow. Surges means basically the spikes, and the rotational losses increases, thereby temperature also increases. The main reason for the cause of huntings are due to sudden variation of load, due to sudden variation of excitation, or due to any sudden fault on the power system, or due to any harmonic load torque. And the side effects of hunting are this is going to make the more electrical and mechanical stresses on the machine, and a huge amount of spikes or surges are going to develop in the current and the power flow, and the rotational losses increases, thereby temperature of the machines are going to get increased. Then how to remove this hunting? So the prevention is basically, the prevention of this hunting is by using the flywheel. So we have to use the flywheel, or by using the damper winding. So we have to use the damper winding, and by designing the machine with high synchronizing coefficient. So these are the three ways we can remove the hunting: by using the flywheel, or by using the damper winding. I've already told you the concept regarding the damper winding. So with the help of damper winding, you can always get the stable region, stable point, even there is a sudden variation of load like that. See, I've already told you induction motor torque, induction generator torque. These things I've already told you. So with the help of this, always you are going to get the stable point of operation. The remaining prevention methods are by using the flywheel, and by designing a machine with high synchronizing coefficient. So these are the three ways by which we can remove the hunting in a given synchronous machine: by using the flywheel, by using the damper winding, and by designing the machine with a high synchronizing coefficient. So finally I can say that hunting means basically you are going to get a new stable point of operation. So how to remove this one? So therefore always you are going to get the main point, which is called as the cause of hunting are due to sudden variation of load, or due to sudden variation of excitation, or due to any fault, or we can say due to even harmonic load torque also we are going to get the hunting. And the effects of hunting are the machine is going to subject to more electrical and mechanical stresses, and the surges are going to develop in the current and the power flow, and the rotational losses increases, thereby temperature also increases. The prevention of hunting is by using the flywheel, or by using the damper winding, and by designing the machine with a high synchronizing coefficient. So let me tell you some important concept in the synchronous machine. As you can see clearly here, it is a stator. So in the stator we are going to keep an armature coil, and we are going to give a three-phase supply. It is basically an alternator. As I have already told you, this is a field winding. So on this field winding, we are going to give a DC supply, and this is called the damper winding. Always the number of turns of field winding is higher than the number of turns of the damper winding. And I have already told you one important point, and if you remember this one, see, listen carefully. The function of the damper winding in synchronous machine, or we can say in the synchronous generator, is only removing the hunting. So listen carefully. The function of damper winding in synchronous generator is to remove the hunting only, whereas the damper winding does two functions in synchronous motor, which is it removes the hunting, and also it is going to provide the starting torque. So these are the two important points that you always have to remember. Whereas in synchronous generator, it does only one function, which is removing the hunting or preventing the hunting. Whereas in synchronous motor, it does two functions. One is it is starting the motor to provide the starting torque, and also to prevent the hunting. So this is a very important point that you always have to keep to understand the concept regarding this one. The function of damper winding in the alternator is to prevent hunting. It is the only one thing it is going to do. Whereas in synchronous motor, it does two functions, which is it is going to prevent the hunting, and also it is going to provide the starting torque. Finally, the function of damper winding in synchronous machine, synchronous generator, is only one thing, which is to prevent the hunting. Whereas the function of damper winding in a synchronous motor is doing the two functions. One is called to prevent the hunting, and the other one is to provide the starting torque. So damping winding is provided in alternator to provide hunting only. So therefore, the damping winding is provided in alternator to prevent hunting only, whereas the damping winding is provided in synchronous motor to prevent hunting and also to provide the starting torque. Because of this damping, the transients are also going to get reduced, and also to suppress the negative sequence field also. So we can even suppress the negative sequence fields. Means simply we can say that the negative sequence components are also going to get suppressed. So we can say it is going to remove the transients, it also going to remove the negative sequence field, it also prevents the hunting in the synchronous machine. So we can say that the damper winding is going to remove the hunting, it is going to reduce the transients, or simply we can say it is going to suppress the negative sequence fields. As I've already told you, the harmonics I've already told you, the odd harmonics I've already told you in a detailed manner, which is positive sequence components, negative sequence components, and zero sequence components also I've already told in the next division class only. But also the transformer also I've already told this concept. But let me repeat this again. Only the odd harmonics, which is n is equal to 6k plus or minus 1, or simply we can say 3m plus or minus 1 also you can easily use. You can go for anything, you are going to get the same result. Their harmonics means k is equal to any integer. So therefore I have already told you n is equal to 6k minus 1, or simply 3m minus 1, or n is equal to 6k plus 1, or 3m plus 1. One more thing is called as the n is equal to 3k or 3m. I have already told these important points. Here m is equal to odd, and here m is equal to even. In this concept I have already told you. See, 3k is called as the triplet harmonics. These are zero sequence, these are zero phase sequence, they won't rotate. Whereas 6k plus 1, or we can say 3m plus 1, these are called as the positive sequence harmonics. They are always going to rotate in phase with the RMF. With the fundamental component, they are going to rotate in the same phase sequence. So it is called the positive phase sequence. Whereas the remaining harmonics, 6k minus 1, or simply we can say 3m minus 1, these harmonics are going to rotate in anti-clockwise with respect to fundamental RMF. So therefore these are called as the negative phase sequence, because they are going to rotate opposite to the fundamental RMF. These things I have already told you. So therefore we can say that the harmonics, the odd harmonics, we can categorize into three types, which is called as the 3m minus 1, or 3m plus 1. For 3m, m is equal to odd, and for 3m minus 1 and 3m plus 1, we have to choose m is equal to even. We can go for even this one also. We are going to get the same harmonics values. So therefore, for 3m minus 1 or 6k minus 1, we are going to get these orbits are called as the negative sequence harmonics, because they are going to rotate in opposite to the fundamental RMF, fundamental flux RMF. And this, it is called as the positive phase sequence harmonics. This 3m plus 1 or 6k plus 1, they are going to rotate in the same phase direction with respect to fundamental RMF. So it is called the positive phase sequence. Whereas 3k or 3m, these have the triple N harmonics, which are, this is not a 6, they are actually basically odd harmonics only. This 9, then it should be 9, because we have to choose only the odd harmonics. We have to choose only the odd harmonics. These are basically zero phase sequence components, because they won't rotate. These things I have already told you in the induction machine concepts only. So zero phase sequence components will never rotate, and the positive phase sequence components, they are going to rotate in the same direction with respect to the fundamental RMF. And the negative phase sequence are going to rotate in opposite to the fundamental RMF. So due to negative phase sequence field, due to negative phase sequence components, or simply we can say due to negative sequence field, the relative speed is very higher, which is n plus RMF negative, because the field with respect to negative phase sequence and the speed of the rotor, they are quite opposite. If this is the speed of the rotor, then this is the speed of the negative phase sequence harmonics. So both are opposite. So therefore, the relative speed is very higher. Thereby, EMF is induced in the damper winding, and it will establish its own flux phi d. With respect to Lenz's law, the damper winding flux opposes the negative sequence field. Therefore, the negative sequence field is suppressed. So we can say that the negative phase sequence field, their rotation and the rotor rotation both are quite opposite. So therefore the relative speed is very higher, because both the directions is reverse or opposite. So therefore the relative speed is very higher. As the relative speed is very higher, the more EMF is going to get induced in the damper winding. So more EMF means it is going to produce the more amount of flux. So it is always going to oppose its cause. Effect is the damping winding flux, and the cause is the relative speed. So therefore it is going to decrease that relative speed by, it is going to suppress that negative field, or we can simply say that whatever the flux produced by this damping flux, it is going to oppose the negative sequence flux or negative sequence field. So we can say the negative sequence field is suppressed. This is the reason by which we can say that negative sequence field is suppressed, because they are quite opposite. So the relative speed is very higher. So we can say more the flux, damping flux. This damping flux is going to oppose its cause. Cause is called as the relative flux. relative speed, so it is going to oppose its the relative speed. With the help of this damper winding, we are going to suppress the negative sequence field. So with the help of damping winding, we are going to suppress the negative sequence field. So for alternator, low resistance damper winding is preferred. But I have already told you, for alternator, we need the low resistance damper winding is preferred to prevent the hunting and also to prevent the negative sequence field. But we need high amount of damper resistance for starting off for producing the starting torque. So listen carefully. The alternator requires the low resistance damper winding is preferred for removing the negative sequence field, or simply we can say to prevent the hunting also. But whereas you need the huge amount of starting resistance or damper winding to provide the starting torque. So let me tell you some important concept here. For cylindrical pole, if R is neglected, then I have already told this important concept, which is for a cylindrical pole, if R is neglected, for cylindrical pole synchronous machine, if R is neglected, then EF is equal to V plus IA into JXS. For symmetrical three-phase fault, we can say that the terminal voltage is equal to 0. Then what is the current? Then ISC is equal to EF by JXS, because the terminal phase voltage is equal to 0. So per phase terminal voltage is also equal to 0. So therefore ISC is nothing but EF by JXS. So this is the equation of the armature current under the short circuit, or we can say under the symmetrical three-phase fault, whenever the terminals are short circuited. So for the same silent pole, if R is neglected, then this is the equation that we are going to get, which is EF is equal to V plus J into IA into XD. So for silent pole, if R is neglected, then you are going to get EF is equal to V plus J into IA into XD. At N is equal to Ns, only XD is taken into account. So therefore, whenever the rotor speed is equal to synchronous speed, we have to take only the direct axis reactance only we have to take, but not the coordinate axis reactance. So just replace XS by XD, you are going to get this equation. So at whenever the rotor speed is equal to synchronous speed, we have to take only the direct axis reactance. So just replace this equation XS by XD. So for symmetrical three-phase fault, I have already told you V is equal to 0, because we are going to short circuit all the three terminals. So V is equal to 0, then IASC is equal to EF by JXD. So this is the equation that we are going to get under this three-phase fault for the silent pole. So therefore, whenever the three-phase fault occurs for cylindrical pole and a silent pole, these are the equations that we are going to get the armature current under this three-phase fault. So we have to replace this XS by XD, because at NR is equal to NS, we have to take only the direct axis reactance but not the coordinate axis reactance. So whatever the current that you are going to get is now, it is always in the D axis, because we are going to take only the coordinate axis reactance, so the current will be also in the same direction. So whatever the current that you are going to get is always along the direct axis, because we are going to take only the XD, so its current will also in the same direction of D axis. So now we'll discuss further important points regarding all the topics of the electrical machines. Just listen carefully. Suppose if V is the rated voltage and variable frequency of a three-phase induction motor speed control method. So basically we are going to give a fixed amount of rated voltage, but the variable frequency which is used for controlling the speed of the induction motor, three-phase induction motor. Then what are the characteristics that we are going to get for whenever the supply voltage is rated and is always constant and the frequency is variable for this three-phase induction motor. If these conditions are applied for a three-phase induction motor, then now you are going to get the different characteristics that we are going to get here. Before analyzing these waveforms, let us know some of the basic equations regarding the induction motor. The maximum torque in a three-phase induction motor is 180 by 2 pi ns into E2 squared by 2 into x2. See, E2 is directly proportional to E1 and E1 is directly proportional to V. E2 is called as RMS value of the per phase voltage of rotor winding, and E1 is the RMS value of the per phase voltage of the stator coil, and V is called as the RMS value of the per phase voltage of the applied voltage, supply voltage of the stator coil. So therefore we can say that here E2 is directly proportional to E1 and E1 is directly proportional to V. So therefore we can say E2 is directly proportional to V. So if you, and Ns is directly proportional to F and X2 is directly proportional to F. So we can say the T mass is directly proportional to V square by F square. But V is a constant because we have given a constant supply. So therefore this T max is directly proportional to 1 by F square because V is a constant. Otherwise it is proportional to V by F whole square. So therefore we are going to get this general equation, which is T max is directly proportional to V by F whole square. But here V is a constant, so therefore we can say it is proportional to 1 by F square. Similarly, the starting torque in a three-phase induction motor is 180 by 2 pi ns into E square R2 by R2 square plus X2 square. As you can see clearly, E is very proportional to E1 and E1 is very proportional to V and X2 is very proportional to F and Ns is very proportional to F. So finally you are going to get which is V by F whole square into 1 by F. So V by F whole square into 1 by F. As a, if V is a constant, then definitely it is proportional to 1 by F cube. So it is proportional to 1 by F cube. The slip at maximum torque is equal to R2 by X2. As X2 is a proportional to frequency, so therefore Sm is inversely proportional to F, or simply we can say Sm is directly proportional to 1 by F. Similarly, Ns is equal to 120 F by P. As you can see clearly, Ns is a function of F only, so therefore Ns is directly proportional to F. Suppose if V is not a constant, then these are general equations. If V is a constant, then we are going to get these equations. Suppose if V by F is a constant, we can see clearly then this overall value is a constant, therefore then the Tmax is always constant for a V by F control, for a constant V by F control. And similarly, if V by F is a constant, then T starting torque is inversely proportional to 1 by F only. And Sm is inversely proportional to F and Ns is directly proportional to F for both V by F control and also for F control. So these are the graphs that you need to always remember these equations, because here this is a very important statements. So based on if V is a constant, then we are going to get these equations. But this is for a general thing. Suppose if V by F is a constant, then the Tmax is constant for a constant V by F control, and the T starting torque is inversely proportional to F whenever the V by F is a constant. So like this, that you need to always keep in mind regarding these things. So now we can say for these characteristics, whenever the frequency increases, the maximum torque decreases, the starting torque decreases, and the slip at maximum torque decreases, and the synchronous speed increases whenever the frequency increases. So as the frequency increases, the maximum torque decreases, the starting torque decreases, the slip at maximum torque decreases, and the synchronous speed will increase. So now we are going to plot these things on this graph. I have already told you it is a torque with respect to speed characteristics. See, whenever the frequency increases, the synchronous speed increases. So therefore you can see the synchronous speed increases. This is the synchronous speed is increasing. And whenever the frequency increases, the maximum torque decreases. So you can see the maximum torque is decreasing. As the frequency increases, the maximum torque decreases. And the starting torque is also decreasing. So you can see the starting torque is also decreasing as the frequency increases. So therefore TST1 is greater than, TS2 is greater than TST3, and TST3 is greater than, TST2 is greater than TST1, and the TM3 is greater than, TM2 is greater than TM1, and F1 is greater than, F2 is greater than F3. Here also, whenever the frequency increases, the slip at maximum value will decrease. So this is SM1 is less than, SM2 is less than SM3. Frequency increases, the maximum torque decreases, the starting torque decreases, and we can say that simply the slip at maximum torque is also decreases, and the synchronous speed increases. So whenever the frequency increases, the maximum torque decreases, the starting torque decreases, the slip at maximum torque decreases, and the synchronous speed increases. So you can see the synchronous speed is increasing and the maximum torque is decreasing and the starting torque is decreasing as the frequency is increasing. So and the slip at maximum torque is also decreasing. These are the things that you can see visualized from this graph. So now we will understand one more important concept, which is called as the single phase capacitor start induction motor. See, single phase capacitor start induction motor means this is said to be a main winding, this is said to be auxiliary winding. So in the auxiliary winding we are going to keep a capacitor for starting purpose only. So after the induction motor is started, we don't need this capacitor, so we are going to use the centrifugal switch. So by using the centrifugal switch we can remove this capacitor when the rotor was given the initial starting torque. For a pure single phase induction motor, the starting torque is equal to 0 because there is only main winding. So to provide the starting torque, we are going to give an extra winding which is called as the auxiliary winding. So for this auxiliary winding, we are going to give a capacitor because to increase the phase difference between the IA and IA, the phase difference increases, the starting torque increases, so we can give more amount of starting torque at the initial condition. So with the help of this, we can provide the starting torque, and after reaching certain speed, with the help of speed sensing centrifugal switch, we are going to remove this auxiliary winding. So therefore we can say that initially it is going to act like a two-phase induction motor, but after some time, as we are going to remove this winding, it is going to now purely act like a single phase induction motor. So V is the single phase supply voltage, it's the phase voltage and the neutral. So I've already told you the current in the main winding is Im and the current in the auxiliary winding is Ia. So T starting torque is either proportional to Im into Ia into sin alpha, where alpha is the phase angle between the Im and Ia. As alpha increases, then this sin alpha increases, so starting torque increases. So that is the reason we are going to use the capacitor to increase the phase difference between the Im and Ia. Direction of rotation can be changed by reversing either main winding terminals or outer winding terminals, but not both. See, if you interchange this main winding terminal, or if you interchange this, basically if you can reverse this one, see, if you can reverse these terminals, then Im will be negative, so therefore this torque is also negative. If you reverse these terminals, then we can say Ia is negative, so again the torque is negative. But if you reverse both of them, negative to negative is positive, so those torque will be the same direction. So therefore, if you want to rotate the direction of the rotor, if you want to reverse the direction of the rotor, you have to reverse any one of the winding, but not both. If you interchange both the reversing it, if you reverse both the terminals, then definitely negative to negative is positive. So therefore, direction of rotation can be changed by reversing either main winding terminals or auxiliary winding terminals, but not both. Direction of rotation can be changed by reversing either main winding terminals or auxiliary winding terminals, but not both. By reversing the supply terminals, both currents Ia and Im are reversed, and hence the torque direction remains same. As I have already told you, suppose if you interchange the supply terminal, then Im and Ir both are negative, so negative to negative is again positive. So therefore, simply we can say that the starting torque will be in the same direction, so it will never change the rotation of the rotor. So by reversing the supply terminals, both currents I and Im are reversed, and hence the torque direction remains the same, so it will never change the direction of rotation of the rotor. So let me discuss some case important one. See, suppose if alpha is equal to 90 degree, alpha is equal to 90 degree means it is a phase angle between the Im and Ia. Then what is the main winding impedance? Main winding impedance is equal to Rm plus Jxm. It is called as the main winding and standstill impedance. And J is called as the auxiliary winding impedance, which is called as the Ra plus Jxa. It is called as the auxiliary winding standstill impedance. Then we can say that this Xc is called as the Ra into Rm by Xm plus Xa, which is equal to 1 by omega c. Xc is equal to, which is nothing but 1 by omega c. So Xc is equal to 1 by omega c. So if you want alpha is equal to 90 degree, alpha is nothing but it is a phase difference between the Im and Ia. If alpha is equal to 90 degree means it is a phase difference between the Im and Ia. Then you know the Im is going to lag by this much amount of angle, which is Xm by Rm. So Im is going to lag the supply voltage by at an angle of Xm by Rm. Whereas this Ia is going to lag by, but you, because in a capacitor also we are going to add the overall impedance of the auxiliary winding is now Ra plus J into Xa minus Xc. So now we have to do the phase difference between them is 90 degree. So by simplification, if you do this one, see, Im is going to lag the phase voltage. The phase voltage is we have an angle of 0 degree if you assume, then Rm is nothing but Rm plus Jxm. So Im is going to lag the phase voltage by an angle which is called as the tan inverse of Xm by Rm. Whereas now the overall auxiliary winding impedance is, which is Ra plus J into Xa minus Xc, because the capacitor is there. So now if you want the phase difference as 90 degree between them, then definitely we are going to get the value of Xc, which is equal to Ra into Rm by Xm plus Xa. So Ra into Rm by Xm plus Xa is equal to 1 by omega c, where omega is equal to 2 pi f. So this is the value of Xc. It is required to keep the phase difference between the Im and Ia as nothing but 90 degree. Xc is equal to Ra into Rm by Xm plus Xa. Then for maximum starting torque, the equations are the, for the maximum starting torque, the equations are, I have already told you, the auxiliary winding theta is equal to tan inverse of Xc minus Xa by Ra. So therefore, theta is equal to tan inverse of Xc minus Xa by Ra, and theta m is equal to tan inverse of Xm by Rm. Then theta is equal to 90 minus theta m by 2. So at this condition, you are going to get the maximum starting torque. So theta is called as the tan inverse of Xc minus Xa by Ra. Theta is equal to tan inverse of Xc minus Xa by Ra, and theta m is equal to tan inverse of Xm by Rm. Then theta should be equal to 90 minus theta m by 2. At this condition, you are going to get the maximum starting torque. So theta is equal to tan inverse of Xc minus Xa by Ra, and theta m is equal to tan inverse of Xm by Rm. and theta is equal to 90 minus theta m by 2. At this condition, we are going to get the maximum starting torque. So let me discuss a small important concept. For example, the synchronizing power for 1 mechanical degree of displacement for a 3-phase 20,000 kVA 6600 volt 50 Hz 12 pole machine having axis is equal to 1.65 ohm and negligible resistance is. In the question they are given the synchronizing power for 1 mechanical degree of displacement for a 3-phase 20,000 kVA 6600 volt 50 Hz 12 pole machine having XS is equal to 1.65 ohm and negligible resistance is. In the question they are given XS is equal to 1.65 and RE is equal to 0 they are given. The armature resistance is 0. And also the synchronizing power equation is 3 delta E square by XS. This is an important formula that you always need to understand, that to remember the synchronizing power is equal to 3 delta E square by XS. So 3 delta E square by XS is called as the synchronizing power. So it is nearly equal to, because E is nearly equal to V, so therefore 3 delta V square by XS. In this question they are given the electrical angle is equal to mechanical angle into P by 2. These things I have already told you. Suppose whenever there is a 1 mechanical degree of displacement, this is 1 degree into the number of poles is 12. So 12 by 2 is nothing but 6 degrees in the electrical. So the amount of electrical angle is 60 degrees. So 6 degrees. Always you have to convert the mechanical degrees into electrical degree. So electrical degree is equal to mechanical degree into P by 2. So always you have to convert the mechanical degree into electrical degree, which is 6 degrees. So whatever the electrical degree you have got, now you have to convert into radians, which is, now do the multiplication by pi by 180. You are going to get in the terms of the radians, which is pi by 30 radians. And I have already told you the synchronizing power is equal to 3 delta V square by XS. So 3 into this delta is called as the amount of displacement. The amount of displacement in the terms of the electrical degrees in radians per second. So this delta is nothing but it is in the terms of the electrical degrees in the terms of the radians per second. So always you have to convert the mechanical degree into electrical degree, and then you have to convert into radians per second. Then that value only you have to use here. 3 into pi by 30 into, see, this is a phase voltage. In the question they are given the line voltage, which is 6600. We are going to assume it is a 3-phase, or you can say star connected system by default, as already they are given a 3-phase. So therefore line voltage is equal to 3-phase. So phase voltage is equal to line by root 3, which is 6600 by root 3 whole square by XS is equal to 1.65. So if you solve this one, we are going to get 921.9 kilowatt. So therefore the synchronizing power is equal to 3 delta V square by XS. As E is nearly equal to V, so therefore 3 delta V square by XS. So delta is called as it is always the electrical degrees in the terms of the radians per second. Electrical degree is equal to mechanical degree into P by 2. So we have converted the mechanical degree into electrical degree, and then in the terms of the radians per second, then we have to use the value of delta in the terms of the radians per second, and V is nothing but the per phase voltage. So in the question they are given the line voltage, so we have to convert into phase voltage, because we are going to assume the connection in the terms of the star connected. So line voltage is equal to 3 phase, so phase is equal to line by root 3. So we can substitute this one in the question they are given. XS is equal to 1.65. So if we solve this one, we are going to get 921.9 kilowatt. So let me discuss another example here. The concept example. The maximum power delivered by 1500 kilowatt 3-phase star connected 4 kV 48 pole 50 Hz synchronous generator with synchronous reactance of 4 ohm per phase and unity power factor. So in the question they are asking that the maximum power delivered by 1500 kilowatt 3-phase star connected 4 kV 48 pole 50 Hz synchronous generator with synchronous reactance of 4 ohm per phase and unity power factor. So they are asking basically what is the maximum power delivered by the 1500 kilowatt 3-phase star connected 4 kV 48 pole 50 Hz synchronous generator with synchronous reactance of 4 ohm per phase and unity power factor. See, always you have to convert the line voltage to phase voltage, which is phase voltage is equal to line voltage by root 3, which is simply 4000 by root 3 is nothing but 2309.4 volt. The line voltage is equal to 4000 volt. And now I want to find what is the line current, because S is equal to root 3 into VL into IL. So therefore IL is equal to S by root 3 into VL, because always we have to assume the star connection. Always we have to assume the star connection if they have not given anything. So therefore S is nothing but the question they have given, which is 1500 into 10 to the power of 3. At unity power factor, as I've already told you, at unity power factor, the value of S is equal to the value of P. So therefore, S is equal to P whenever the unity power factor is considering. So therefore, unity power factor means cos theta is equal to 1 means theta is equal to 0. At that condition, we can say that part of the active power is equal to complex power, which is 1500. So 1500 into 10 to the power of 3 by root 3 into VL is 4000. In a star connection, the line current is equal to phase current is equal to 216.5 amperes. As it is a synchronous generator, the EMF induced per phase is equal to under root over V cos phi plus IA RA whole square plus V sin phi plus IA XS whole square. It is actually all these values are the per phase voltage only. All these are the phase voltages, per phase diagram. So therefore, all these are the phase values only. So therefore, this is the EMF equation of synchronous generator. Plus for the lagging load, minus for the leading load. All these things I have already told you. Plus for the lagging load and minus for the leading load. As in the question they are given, the power factor of the load is nothing but unity power factor. Because it is simple generator, the power factor of the load is nothing but unity power factor. So therefore, this is actually phi or theta. Generally in the formula I have told you it is a theta, which is V cos theta plus IA RA whole square plus V sin theta plus IA XS whole square. I have already told you that phi is equal to theta. Actually, theta is called as a power factor angle between the V and IA. These things I have already told you. So therefore, this is called as the actual theta. You have to replace this phi by theta here. This is the general expression. So therefore, now you can see the terminal per phase voltage just now we have seen, which is 230.9.4, and the power factor is unity into 1 plus. Here, as I have already told you, in the question they have not given anything regarding the RA. So we are going to assume it as 0. Plus, here again, as the load has unity power factor means sin theta is equal to 0. So 0 plus. Here IA value just now we have seen this, which is equal to per phase current only, which is 216.5 into the value of XS. In the question they are given synchronous reactance value is equal to 4 ohm. 4 ohm they have given already 4. So if you solve this one, we are going to get which is 2466.5. This is the per phase voltage which is induced in the generator. Which is the per phase voltage which is induced in the generator. But this is the phase voltage, but we need the line voltage. So line voltage is equal to root 3 into phase voltage. So if you solve this one, we are going to get 4272 volt. So this is actually theta. There is nothing like phi. Phi concept I have already not told you. So this is actually theta. So therefore we can say now the equation of the power. Power is equal to, here I have already told you, EL into VL by XS into sin delta. So now we have to use the line voltages concept. The overall, we can say the overall active power generated, by this three-phase induction, by this three-phase synchronous generator is equal to EL into VL by XS into sin delta, where EL is called line voltage of the induced voltage of the generator and VL is called terminal line voltage. EL is the generated line voltage and VL is the terminal line voltage by XS. These are value of the maximum power. So maximum is equal to EL VL by XS. EL value we know, which is 4272 into VL value in the question they have given 4000 by XS is equal to 4. So if you solve this one, we are going to get 4272 kilowatt. So this much amount of maximum power which can be delivered by this synchronous generator. I have already told you, in a synchronous generator, EF is equal to V plus J into IA into ZS. ZS is equal to RA plus JXS. In this question they are not given RA, so we have to assume RA is equal to 0. So therefore, in the question they are given XS is equal to 4. In the question they are given XS is equal to 4. And I have already told you theta is the phase angle between the V and IA. It is not phi. So theta is the phase angle between the V and IA. These things I have already told you. So therefore, the maximum power which is generated by this three-phase synchronous generator, which is EL VL by XS. EL is called as the line voltage EMI which is generated, and VL is the terminal line voltage by XS. In this question, basically they are given the terminal line voltage they have given. So first we have converted to phase voltage. The terminal phase voltage we have converted, and then we have figured out the phase current or line current in star connection. And the EMF equation which you already know, per phase values we know, this is the equation. So by substituting these values for this amount of unity power factor load, then we are going to get unity power factor means it's a power factor angle between the terminal voltage and terminal current, which is V comma IA. So based on this we have calculated the per phase induced voltage. As the star connection, then we have calculated the line voltage induced EMF. Then we have studied about the maximum power, which is EL VL by XS. By substituting those values, we got the maximum power. This much amount of maximum power which can be generated by this three-phase synchronous generator. So let me tell you some important concept, which is single phase power equation is equal to A phase into V phase by XS into sine delta. It is a per phase diagram. So for per phase diagram, we are going to get the power in this way. But if you want three phase power, just you have to multiply by 3 because there are 3 phases. So 3 into single phase. But I have already told you in the star connection, the line voltage is equal to 3 phase voltage and line voltage is equal to 3 into phase. So EL is equal to root 3 into E phase and VL is equal to root 3 into V phase by XS into sine delta. So you are going to get 3 into power single phase. So therefore you can say that simply here, this is the overall 3 phase power you are always going to get, which is EL into VL by XS into sine delta. This is for the single phase and this is for the 3 phase. So if you want single phase, just use the phase values. But if you want 3 phase power, just use the line values. So like this you are going to get this equation. And now if you want the 3 phase maximum power, if you want the 3 phase maximum power, which is nothing but EL into VL by XS. So overall 3 phase maximum power is equal to VL into EL by XS. So now we'll discuss another concept through example. Suppose a 3-phase star connected synchronous generator. A 3-phase star connected synchronous generator has synchronous reactance XS is equal to 5 ohm per phase. 3-phase star connected synchronous generator has synchronous reactance XS is equal to 5 ohm per phase. It delivers 12 kVA load at a unity power factor. The terminal voltage is 2000 volt per phase. The induced EMF per phase of the generator is. So we have to find what is the induced EMF per phase. We need to figure out for this. A 3-phase star connected synchronous generator has the synchronous reactance XS is equal to 5 ohm per phase. It delivers 12 kVA load at unity power factor. The terminal voltage is 200 volt per phase. The induced EMF per phase of the generator is we need to figure out. As I have already told you, S is equal to root 3 VL IL or 3 into V phase into I phase. So I phase is equal to S by 3 into V phase. S is nothing but in the question they are given 12 kVA. So 12 into 10 to the power of 3 by 3 into the terminal per phase voltage is 200. They have already given the terminal voltage is 200. So therefore if you solve this one, we are going to get the phase current is equal to 20. So therefore E phase is equal to, so E phase is equal to, I have already told you, E phase is equal to V phase plus J I phase into XS. So now E phase bar is equal to, you can see clearly here, I phase value we know which is 20 and XS also they are given which is 5. So therefore 225 is nothing but 100J plus, so V phase we are going to assume, V phase is equal to, they are given 200. So 200 at an angle of 0 degree and this is 100 at an angle of 90 degree plus 200 at an angle of 0 degree. So if you do the magnitude value, we are going to get under root over 100 square plus 200 square. We are going to get just nothing but simply you are going to get root 5 into 100. So this much amount of per phase induced voltage that we are going to get. And the per phase current is equal to 20 at an angle of 0 degree. So per phase current is equal to 20 at an angle of 0 degree. And as I have already told you, the load is a unity power factor. The load is a unity power factor. So therefore, the terminal voltage is equal to the terminal per phase voltage is equal to 200 at an angle of 0, and the terminal current is also equal to 20 at an angle of 0 degree because both are in phase because it is a unity power factor load. So V phase I phase is equal to 0 degree. It is actually the terminal voltage. So theta is the angle between the V and IA. So V is called as the per phase terminal voltage and IA. As you can use even this equation also to get the value of the EMF induced per phase, which is V phase into cos theta plus IA into RA whole square plus V phase into sin theta plus IA into XS whole square. See in the question, they have not given anything regarding the RA, so we are going to assume that 0. Then we are going to get unity power factor means cos theta is equal to 1. So we are going to get V phase whole square plus here as theta is equal to 0, sin 0 is equal to 0. So we are going to get here 0 IA into XS. IA is nothing but just now we have seen it is equal to phase current 20 and XS is equal to, we are going to get which is already they are given is equal to 5. So 5 into 20 is nothing but 100. So 100 whole square. So simply it is a magnitude of the V phase is nothing but 200. So 200 whole square plus 100 whole square. Same thing we are going to get which is 100 into root 5. So this is the general formula that you always have to keep in mind here. So theta is the angle between the V and IA. As theta is equal to 0 because the unity power factor load, So therefore we can say V and I are in phase with respect to each other. If V is equal to 200 at an angle of 0, then I is also 20 at an angle of 0. That is what I am trying to tell you. Let me tell you a small concept through example. A three-phase induction motor has a starting torque of 200 nanometer, 200 Newton meter when switched on directly to supply. If an auto transformer with 50% tapping is used for starting torque would be. Suppose in the question they are given a three-phase induction motor, see DOL means direct online, means we can say that it is connected in a delta fashion. It is connected, see, direct online means the stator is connected in the delta fashion. So therefore, what we are going to get basically, if you are going to use the delta connection, DOL means we can say it is a delta connected, stator is always connected in the delta. So therefore now, here what we are going to basically, simply we can say that a three-phase induction motor has a starting torque of 200 Newton meter when switched on directly to supply. If an auto transformer with 50% tapping is used for starting torque would be. Then the starting torque with respect to auto transformer is equal to F square into starting torque with respect to DOL. Then the question they are given, the starting torque with respect to DOL is nothing but 200 Newton meter and the percentage of tapping is 50%. You have to convert into numerical value which is 0.5. If the starting torque with respect to auto transformer is equal to 0.5 volts into 200, so you are going to get 50 Newton meter. So starting torque with respect to auto transformer is 50 Newton meter. See, always the starting torque is always directly proportional to phase voltage whole square. So phase voltage whole square. So with the help of auto transformer, we are going to get the decrease of phase voltage. As you can see clearly here, the starting torque is directly proportional to phase voltage whole square. So for starting torque with respect to DOL means simply we can say direct online means the stator is connected in the delta fashion. So directly we are going to give the supply. So we are going to get V phase whole square. But if you use the auto transformer with the help of tapping, we can reduce the phase voltage. Let me assume we are going to reduce the phase voltage is equal to X times the initial value, because with the help of tapping, the voltage is going to get decreased. The per phase value is going to get decreased by a factor of X into V phase whole square. So if you divide these two equations and if you simplify, we are going to get the starting torque with respect to auto transformer is equal to X square times the starting torque with respect to DOL. So with the help of auto transformer, we are going to reduce the per phase voltage by a factor of X. Then we are going to get this important relation which is equal to the starting torque of auto transformer is equal to X square times the starting torque of the direct online, means the stator is connected in the delta fashion. Let me tell you another concept. For example, a three-phase 2000 volt star connected wound rotor induction motor has the following no load test data, which is 2000 volt, 15.3 ampere and 10.1 kilowatt. The core loss resistance of the approximate equivalent circuit is nearly we need to figure out. So basically in this question they are given a three-phase 2000 volt star connected wound rotor induction motor has the following no load test data, which is 2000 volt, because at no load test we have to give the rated voltage, which is 2000 volt. It is similar to a open circuit test on a transformer. So remember, the no load test on a rotating machine is nothing but it is open circuit test similar to open circuit test of transformer, and the block rotor test on the rotating machine is equal to short circuit test on the transformer. It's a very important point. Listen carefully. The no load test on rotating machines is equal to open circuit test on a transformer, and the block rotor test on any rotating machine is equal to short circuit test on a transformer. It's a very important concept. So therefore, at no load we have to give the rated voltage, which is 2000 volt. Then we are going to get a very small amount of current, which is 15.3 ampere, and we are going to consume a 10.1 kilowatt amount of power is consumed by this star connected wound induction motor. The core loss resistance RC of the approximate equivalent circuit is, so we have to find what is the value of the approximate equivalent circuit diagram of that. What is the core loss resistance of the approximate equivalent circuit we need to figure out. So the approximate equivalent circuit per phase diagram, the per phase of approximate equivalent circuit of induction motor is, this is RC, this is JXM, this is R01, this is JX01, this is R2 dash into 1 by S minus 1. See, at no load, NR is nearly equal to NS. So slip is equal to NS minus NR by NS, as slip is nearly equal to 0. So 1 by 0 is nothing but infinity. Infinity minus 1 is again infinity. So therefore you are going to open circuit this one. So therefore this is nothing but it is an open circuit. Only this circuit is we are going to consider at the no load condition. And the see R2 dash into 1 by S minus 1 is nothing but infinity. The equivalent circuit at no load condition is. So we have to open circuit this one. So this is the thing that you are going to get. So V1 is nothing but per phase voltage, but we have given the line voltage of 2000. So per phase is equal to line by root 3, which is 2000. This is 2000. This is actually 2000 by root 3. And here the amount of power consumed, it's a per phase diagram. It is a per phase diagram. So we have to consider for single phase. In the question they are given a 3-phase power, but we have to go for the single phase because it is a single phase diagram. So therefore P1 is equal to 10.1 into 10 to the power of 3 by 3, because 10.1 kilowatt is for 3 phase, but we want only for single phase as per the per phase diagram. So therefore by root 3 by 3 we need to do this one. So therefore if you see clearly, then what is the this inductor is not going to consume any active power, only the RC is going to consume the active power. So power consumed by this RC is equal to, which is V1 square by RC. So therefore if you reverse this one, we are going to get RC is equal to V1 square by P1. V1 is nothing but 200 by root 3, and P1 is equal to, this is actually 2000. It's actually 2000. So therefore now if you substitute V1 is equal to 2000 by root 3 and P1 is equal to 10.1 into 10 to the power of 3 by 3, and if you solve this one, we are going to get 396 ohm. So therefore RC is equal to 396. Means here whatever the diagram is a single phase diagram or per phase diagram, so we have to consider all the phase values only. We have to consider per phase values only. We have to consider. So V1 we have considered the phase value, and the P1 is also per phase power, which is 3 phase power by 3. So if you substitute these values and if you do simplification, we are going to get 396 ohm. So let me tell you some important concept regarding this DC shunt motor. See, this is the basically DC shunt motor. So this is the supply voltage or the terminal voltage we are going to give supply, which is constant. We are going to assume it as a constant value. And this is the current, supply current IL, and this is the shunt current, and this is the armature current. This is the armature resistance, and this is the back EMF EB. Where R is called shunt resistance. Then during no load, suppose if you are not going to keep any load, then simply we can say that no amount of useful power is done, so therefore the output power is equal to 0, or simply we can say the shaft power is equal to 0. So whatever the torque developed, the power developed is equal to output power plus some rotational losses, because whatever the electrical power developed at this terminals is equal to some output power plus some rotational losses. As the output power is equal to 0, because we are not going to count any useful things, so therefore output power is equal to 0, then the whatever the power developed is equal to the rotational losses. So therefore whatever the power developed here, it is equal to the rotational losses, which is EB into IA is nothing but it is equal to the rotational losses, because there is no output power, because electrical power developed is equal to the output power plus rotational losses, as you can see clearly from the power flow diagram. So therefore as output power is equal to 0, so whatever the power developed is equal to rotational losses. So therefore the power developed is equal to rotational losses. Power developed is equal to EB1 into IA1 for case 1. So therefore EB1 is nothing but VT minus IA1 into RA into IA1. See, N1 is called as the no load speed. So therefore the power developed is equal to EB1 into IA1 is equal to, EB1 is nothing but simply, suppose case 1 which is VT is a constant, so therefore VT minus IA1 into RA into IA1, where N1 is called as a no load speed. At no load, the rotor is going to rotate at a speed of N1. Suppose during loaded condition, then what is going to happen? Now we are going to see. See, during the loaded condition, the efficiency is nothing but output power by input power. See, output power is equal to input power minus losses by input power. So losses is equal to, losses means simply we can say, see, the losses means simply we can say input power minus output power. See, always we can say that input is equal to output power plus losses. Input is equal to output power plus losses. So therefore losses is equal to input power minus output power. See, as the output power is equal to 0, then definitely we can say whatever the input power should be always equal to losses. See, listen carefully here. The power loss is equal to input power minus output power. See, what are the losses in the machine? So during the loaded condition, output power is not at all equal to 0, but at no load, the output power is equal to 0. But during the loaded condition, the output power is not at all equal to 0. So power loss is equal to input power minus output power. See, the losses which are present in the DC machine are the rotational losses, field losses, plus armature losses, plus stray losses. So these are the losses which are going to present in the shunt machine. So therefore, it is called rotational losses plus field losses. Field losses means simply we can say that this is a field copper loss and the armature copper loss, or simply we can say initially it is called as a copper losses. It is called as a copper losses. The rotational losses plus field copper loss plus armature copper loss is called as the total copper losses. Then we are going to get the stray losses. There is also one more thing which is called as the stray losses. We are going to get the rotational losses, the copper losses. Copper loss are two types, which is called as the field copper loss and the armature copper loss, and also we are going to get the stray losses. So input power is equal to V2 into IL2 for the case 2 during the loaded condition. Then EB2 is equal to VT minus IA2 into RA. N2 is the speed during the loaded condition. So N2 is the speed during the loaded condition. So conclusion is, as the VT is a constant, IH is constant, so flux is also constant. Then we can say that EB is directly proportional to N into phi. N into phi. So therefore EB1 by EB2 is equal to N1 by N2. So now what is the value of, see if you see clearly EB1 and EB2. See EB1 is nothing but VT minus IA1 RA. Whereas EB2 is equal to VT minus IA2 RA. As the load increases, current IA increases. So therefore this drop will decrease. So therefore EB2 value will decrease here. So therefore, whereas EB1 is very higher when compared to EB2, because as the load increases, the current increases. So drop across the armature will increase. So therefore EB value will decrease. So therefore we can say that EB1 is greater than EB2. So therefore here also same thing, N1 is greater than N2. So therefore the no load speed is greater than the loaded condition. It's a very general case, we can say clearly. So no load speed is N1 and the speed during the loaded condition is N2. So we can easily see from this equation EB1 is greater than EB2. So therefore N1 is greater than N2 always.